Hello everyone, my name is Zhou Jianjing and I'm from Qingdao University. And before starting my presentation, I would like to thank my advisors, Professor Gao and Professor Pidrosia on NAS, because they always give me help with this paper. And then the topic which I'm going to talk about is a cooperative differential games with continuous updating using Pontryagin maximal principle. This is a new approach for the differential game. It is a continuous updating, and the content is divided into 4 parts. The first part is for the introduction about the initial game model, and the second part is to introduce our continuous updating approach. And the next part is to present the main method which we use is the Pontryagin maximum principle with continuous updating. And the last one is to illustrate the example of pollution control problem. So let's start with the introduction. In the initial game model, we consider an n-player game, and the motion equation is defined on the interval from T0 to the capital T, and we define the payoff of each player and the integral from T0 to the capital T. The general assumption is HI is an integrable function. Next, we turn into the cooperative game. We see U star is the optimal strategy if it can maximize the total payoff of n players defined on the interval from T0 to the capital T. And we denote the L and the set of imputations in the game. It should satisfy 2 conditions. The first condition is a collective rationality, and the second is for the individual part. And M is a set of the cooperative solution. It is also the set of the imputation set L. And then we go forward to introduce the method of continuous updating. But the problem is, why should we construct the continuous updating? Because in the classical differential game, the model is constructed based on the idea about all players know everything and use the information on the whole time interval, which cannot be true in the real life. So we present the method of continuous updating because it is more realistic. And we can see from the figure 1, here are some assumptions about the continuous updating approach. From the figure 1, we assume that at each time instant t, the players have information about the motion equation and the payoff function only on the interval from t to t plus t dash. And we call t dash is the information horizon. So and each time t, the player has the information defined on the interval t dash. T dash is the information horizon, and as time goes on, players continues receive the update information about the motion equation and the payoff function. Next, we consider 2 intervals. One of them is the interval from t to t plus t dash, and the next is the t plus epsilon to t plus epsilon plus t dash. We can see from the figure 2, and at each time instant t, if we want to get the optimal control U star t, we need to consider the information horizon on t from t to t plus t dash. If we want to get the optimal control and the instant time t plus epsilon, we should consider the information horizon based on the interval from t plus epsilon to t plus epsilon to t plus epsilon plus t dash. And here is a list that related to our approach, which continues updating.
I can say a few words, just few words about this paper. So on this slide and the next slide, you can see the list of papers that are related to the continuous updating approach, that are related to continuous updating approach, and some other related results. So actually, the papers for continuous updating now cover the linear quadratic case with autonomous model and non-autonomous model, non-cooperative cooperative, Hamilton-Jacobi-Bellman equations, and as well as this work is about the Pontryagin maximum principle, and now the cooperative case and non-cooperative case as well. And also below the last link that you can see is the link from the IFAC 2020, which is the title is the optimal control, inverse optimal control with continuous updating for human behavior modeling. This in some sense shows the application of continuous updating approach to the engineering systems of or like a driving a system, which is and yeah, in some sense, it's an interesting application of continuous updating approach. On this slide, you can also see the other links and also the list of related links of the authors that have studied a similar problems in control theory and in differential games where they have tried to construct an optimal control, a stabilizing optimal control, where the idea of how to construct optimal control is very similar to the idea that we use in our work. And therefore, it's very important to mention. Other than that, there is a in this list, you can see a paper which is also contains some results related to the results that we present here for the linear quadratic case. Yeah, and I think this is it. Okay, thank you very much. Thank you. Please
thank you for your comments. Thank you. And let's move on. This is a subgame with continuous updating. And we should mention that at each time instant t, the subgame is defined on the interval, from t to t plus t dash, and xt dot s is a derivative with respect to s, and also the payoff of the player I for the subgame is defined on the interval, also from t plus t dash. We see that XTS and UTS are trajectories and strategies in the game. And then we define the strategy profile U star T with continuous updating. If we call U star T is a cooperative strategy with continuous updating, if it is defined in the following way, U star T is corresponding to U star TS when S is equal to T, and U star TS is U star TS is obtained by maximize the total P of n players defined on the interval from T to T plus T dash. The trajectory X star T is obtained by using U star T and the motion equation 1. Then the next part is to discuss the method which we use to derive the optimal control and trajectory, the Pontryagin maximal principle with continuous updating. So the Hamiltonian function for the Pontryagin maximal principle, when we fix our t, the Hamiltonian function ht is defined as the payoff of all players in the subgame. Here, hi is an instantaneous utility, and f is the is from the motion equation, and our psi t is a constant variable. It is a classical definition for the Hamiltonian function. Next, let's construct the theorem of the Pontryagin maximal principle for cooperative strategies with continuous updating. And this is a classical theorem, but the difference is that in our case, at each time instant t, the game is defined on the interval from t to t plus t dash. So the time variable s should defined on the interval from t to t plus t dash. And for the time, it is limited, so I won't go into detail with this theorem. If you are interested, we can discuss about it later. And in the cooperative game with continuous updating, the essential definition is to define the characteristic function with continuous updating. The function Vs is a characteristic function with continuous updating if it satisfies the formula 8. And we should mention that V is a function of our state and the instant time t and the time t. Here we tau s. We tau s is a characteristic function in the game defined on the interval from our s to t plus t dash, and the construction of the VTS is in the paper of Professor Bidoloxian and Professor Zakor. The last part is the example of pollution problem by using continuous updating approach. The initial problem is there are n players or n countries. They should decide how much pollution is emitted to the air. Xt is the stock of pollution and the time t, and the motion equation has the form of the following linear equation. UIT is the pollution, the player I emitted to the air. Delta is our absorption rate of pollution by nature. So for simple case, we assume that delta is equal to 0. And the payoff of player I is defined as following. Here Bi minus 1 divided by 2 Ui multiply Ui is we can see H and the income from the production, and the DRX is the cost by overcoming the pollution. So this is a formula. This is a classical pollution problem. And then for the for a fixed time t, the family of subgame with the duration t dash has the form and the motion equation. The motion equation of the subgame gamma x t plus t dash starting and the state x should have in the following equation, and the payoff of player I divided on the interval from t to t plus t dash. It's defined in the formula 11. In order to get the cooperative strategy with continuous updating, we need to solve the optimization problem, which is stated in the formula 20. We need to maximize the total payoff of n players on the time interval from t to t plus t dash. And the method which we use is the Pontryagin maximal principle. So the corresponding Hamiltonian function is defined as the equation 30. According to our procedure, we construct the open loop optimal cooperative strategy with continuous updating. U star t is equal to Ui t star ts when s is equal to t. And by substituting the Ui star t into our ordinary differential equation 10, we can get the cooperative trajectory x star t with continuous updating in the following case. And here is a graphic result. Here is a graphic results for cooperative strategies and cooperative trajectory. We can see in the figure 3, the comparison about the cooperative strategy between the continuous updating is a blue line, and the initial case is a red line. So we can see that the optimal control with continuous updating is more stable. It not even change when time goes on. And first, we can see that the players under the continuous updating approach try to emit the pollution as much as possible because they do not forecast their actions on the whole time interval, but they only focus on the local information and try to emit as much as possible. So this is the reason why here it is more. And for the pollution accumulation finger, starting from t is equal to 0 to t is equal to 8, the pollution accumulation in the initial game model is a red line, is less than the model with continuous, because in the initial game model, players are more knowledgeable, we can see that, and they know the information from the whole time interval, which can lead to the lower pollution because players are cautious. And here is the explicit form of our characteristic function and Shapley value with continuous updating. The same as the graphic results for our characteristic function and Shapley value, we can see from the figure 5 demonstrate the reason why the value of characteristic function in the initial game model is greater than the case with continuous updating, because the complex of the information with continuous updating can reduce the effective of the collision. So in the continuous updating, the value of the characteristic function is lower. And we should notice that the continuous updating case is more realistic. This is more close to the real life, and the same as the Shapley value. So that's all for today. Thanks for your attention.
Thank you very much. Thank you. Anyone has any questions?
I have a question. In your example in pollution control, why you need to update information? You know the dynamics, you know the payoff. Why you need to apply this approach? Update.
Yes. In the initial game model, the assumption is we know the information about our motion equation and our payoff function on the whole interval, on the whole time interval, but in the real life, it's not possible to know all this information for the whole time interval.
Why you have all information here? You have dynamic, you have payoff. What do you know about the system?
I can help. I can help here to answer. Exactly. In this particular model, we can see that the right-hand side, the function under the integral is actually not changing in time. So in some sense, this is called the autonomous model. Yes. And of course, we can say that we know everything from the beginning till the end of the game, but the additional meaning of the continuous updating approach, or additional reason to apply it, is that sometimes even if we know all information from current time instant t till the end of the world, even if we know it, we do not use it. Or even if we know it, we're not able to calculate of what is going to happen until the end of times or until some long time interval. So this is one reason, yes, that why we decided to use this example, because it's classical and because it, in this sense there is no problem. And another thing is that we actually wanted to compare the solution of the classical model, well, all information is known, and the model with continuous updating. In this way, to show the difference and to show that actually when we apply continuous updating, the complexity of calculations is not changing. And we just wanted to show that the solution is also simple to obtain, as simple as in classical. I don't know if I helped to answer. I hope so.
But if you apply this approach, for example, for this model, you need to take in mind transversality conditions. And transversality condition, if you consider, for example, this problem in infinitive time, it will be different from the finite interval. So have you some example which in which this approach is not working?
Well, in our case, I'm not very clear, but in our case, the transversality conditions are related to the last point of the interval.
Yes, but if you consider, for example, this problem in infinitive interval, transversality condition will be completely different. So in this case, maybe if you will apply this approach, you will never obtain optimal behavior. So if, it is interesting to find here an example which contradicts to this approach.
I'm not clear about the first part. I cannot understand, but the second, yes, this is. It's very important not to show that it is good to use this approach, but also important to show when this approach does not make sense.
Yes.
Yeah, I understand. Yes, thank you for the comment. I think that is important motivation for even to define the class of problems where, in some sense, some economic. Yes, that's what you mean. Yes, some.
Yes.
Yes, this is very good. Thank you very much. This would improve our work substantially. But for transversality conditions for infinite case, actually it is possible. Continuous updating approach also possible to apply when at every current time instant t we look ahead for infinity. And again, nothing. Not much difference. We still can obtain the solution, still can construct like this. So we still can construct the so-called resulting Nash equilibrium and so on, using the infinite t dash. But we never presented this in any work. But anyway, but what do you mean, Baba?
No, I mean that the transversality conditions for infinitive case and for finite case are different.
Yes.
So it's the main point here.
Yes. Oh, okay. We will think about this. Thank you very much for that's very important idea. That would make the research complete. No, not complete, but additional. Yeah. Thank you very much. Thank you. Anyone else has any questions for? So if not, then maybe we could go to the next speaker. Thank you very much for a great presentation. Thank you.